Welcome back. In the second part of this section, we're going to look at another numerical method called Simpson's rule. Uh, but before we get to that, let's take a look at this little theorem that we've got here. And it's kind of a fun one. Not super useful for everyday use, but actually it fits into Simpson's rule kind of nicely. We've got our function that happens to be a polynomial of degree no more than 2. So in other words, f of x either is some sort of straight line or it's a parabola. And we've got two intervals that are side by side and of the same length. So it doesn't matter what the length is, but they're just the same for both. If we wanted to know what the definite integral is from beginning to the end, then we just have to use the following formula, and it's just the total distance over that interval divided by 6 times the y values at those 3 points. The y value at the beginning plus the y value at the end plus 4 times the y value that's right in the middle. A couple of things I wanted to say about this, and this is sort of going to set the scene for Simpson's rule. Pretend, if you will, that you actually did have a polynomial and it was of degree no more than 2. So let's pretend just for fun that we had ourselves a parabola and we wanted to find our area under the curve, and we were going to start at x0 and we were going to end up at xn at some point off in the distance. And so what I might do is slice it and partition it, and so on. And so that I would be able to basically look at this in groups of 2 and find the area in groups of 2 using the theorem. Because I'd have between x0 and x2, I could use that formula for those 3 points. And then between x2 and x4, I could use those 3 points. So in other words, if I wanted to find the area all the way under the curve from the very beginning, from x0 to xn, or in other words, from A to B, if this was a parabola, then I could just say, well, if I wanted to go from A to B, then I'd have all those little chunks of 2 that I could just basically use this formula again and again. I could say, well, x2 minus x0 over 6 plus times f of x0 plus 4 f of x1s plus f of x2, and then do the same thing with the next interval. So that's from x2 to x4. And then it would be f of x2, 4f of x3, and plus f of x4. And I could continue on in that pattern all the way until the end. And then I could say something else further. If we've done this as a regular partition, then these numbers that are in front are actually going to be the same, right? I could say I know that if I took my whole interval from A to B and partitioned it, then the width of one little interval, that's delta x, that's b minus a over n. Then for 2 intervals, or 2 little subintervals, the width should be 2 times b minus a over n. So this really could be replaced with 2 times b minus a over n. And I could do that with the next and the next and the next after that. Once I've done that, then I could take that 2 times b minus a over n and factor it out of everybody. And the 6 in the denominator, factor that out of everybody. And then all I would have is a bunch of f of x1s, x2s, and x3s, and so on. I'll notice that a lot of them would be 4s, all the ones that are in the middle, the x1, the x3, x5, and then some of them, there'll be 2 of them. F of x2 will show up twice because it shows up at the end of one group of 2 and shows up at the beginning of another group of 2. Same thing with f of x4 because it shows up as the end of a group of 2 and is at the beginning of a group of 2. And then at the very last and the very beginning, those ones show up exactly once. So I could come up with actually a nice exact formula for the area under a quadratic function. And you might be saying to yourself, well, okay, that's great, but we already know how to integrate a quadratic function. So here's the idea that brings us into Simpson's rule. So we could say to ourselves, well, anytime you have 3 points, you can get a polynomial that passes through those 3 points, and that polynomial will be a polynomial of degree 2 or less. So pretend, if you will, we had ourselves our function, and it didn't really matter what our function looks like. It could be a polynomial or not. But when we do our partition, x0, x1, x2, and we take those three y values, we could say, well, whatever those y values are, there's going to be some sort of parabola that would fit through them. And if I find the area underneath the parabola, that'll be close enough to the actual area under my curve. So basically the idea here is, for Simpson's rule, we are going to be partitioning things into some subintervals, and for each group of 2 subintervals, we're going to be imagining that those y values are on some parabola or potentially some straight line, and then we use the previous theorem to figure out the area underneath that parabola or straight line and say that that's approximately equal to the area under our curve. So the one little side note here is, of course, since we're doing our intervals in pairs, then of course you have to have an even number of subintervals. If you split things into n equals 7, then you would be out of luck because you wouldn't be able to have groups of 2. And so the theorem that we have now for Simpson's rule says that, again, you've got yourself a continuous function. In other words, it has a definite integral, and we've got ourselves an even number of subintervals. Simpson's rule says how we do that is, as I said, a bunch of 4s and 2s and 4s and 2s of all the ones in the middle of all the y values, and that the beginning and the end y values show up exactly once. The number that's in front, this b minus a over 3n, that came from, remember that our distance that we had between our x values was originally written as x2 minus x0 over 6 and x4 minus x2 over 6 and all the rest. This is the same thing as 2 times delta x. That's the width of 2 subintervals, which is 2 times b minus a over n. So what we wind up with is 2 times b minus a over n times 6. The 2 and the 6 cancel, leaving the 3. So that's where that part of that formula comes in. Same thing as with trapezoidal rule. The Simpson's rule tells you that if you have n going to infinity, that this approximation is going to approach the definite integral. So if you decided to use Simpson's rule to come up with a formula in terms of n for what is the definite integral, and then use limits, you can actually find a numerical value for that definite integral without needing to actually know what the antiderivative is. So now we're going to use Simpson's rule to do the same definite integral as before, same number of subintervals. So again, I know what my y values are. My y values for that interval was 1 and 4/5 and 2/3 and so on, same as before. So I can go right ahead and just use my Simpson's rule and say to myself, well, number 1, b minus a over 3n, I should really calculate that. That's 3 minus 1 over 3 times 8. That's 2 over 24, or 1/12. And so now Simpson's rule says if we want the definite integral from 1 to 3 of 1 over x dx, that will be approximately 1/12 times, 1 times our first y value, plus 4 times the next, plus 2 times the next, and then 4 times the next, 2 times the next, 4 times the next, 2 times the next, and 4 times the next. And then we're on our last one, and the last one is just 1 times the last one, and the last one was 1/3. So when I run that through my calculator, I get 1.0 0.9872539. That's what I got on my calculations from my calculator. And again, reminder that for the exact value that we had, it's actually really close to that. The actual value for the definite integral of 1 over x dx is 1.0986, So it did an even better approximation than the trapezoidal rule did. Trapezoidal rule gave us 1.10, which was pretty close, but here we're actually the same for the first three decimal places. So this is actually a really good approximation.